Next up, we have Andrea Di Biagio telling us about subsystem locality.
Thank you. Thank you, Catherine. Thank you, organizers, for inviting me. So today I'm going to talk about the relationship between two notions of locality. And I think this is fitting because it's a relativistic quantum information conference, right? And one notion of locality is the relativistic notion of locality, which is related to the fact that there is a finite speed of light, and information cannot travel faster than the speed of light. And this is a space-time notion. It's a geometrical notion. So we have space-time is, we have different regions of space-time, and we can characterize whether information can flow from one to the other using this causal structure that comes from it. And then there's a related notion of locality, which is the one often used in quantum information theory and quantum foundations, which for the purposes of this talk I will call subsystem locality. And it's got to do with how information travels through systems. So whereas on the space-time case, as I said, it's connected to space-time regions, over here the notion is anchored on the notion of subsystems. This is, for example, a two-local, I would say, like a two-local circuit where every gate only acts on two systems at a time. This also has a way of how information propagates in a system. And often, they strike as similar things, but they're not the same, right? For example, in quantum field theory, a field is a very delocalized thing, but it's one single system. So a local gate on the field doesn't have to be localized in space necessarily. A place where the relationship, or the difference between those two things is relevant is on some theorems about low-energy quantum gravity that Marius and Thomas already mentioned. So there are these theorems, these generic arguments for why if we detect that gravity was able to create entanglement between two masses, then these theorems say, well, gravity cannot be both classical and local. And this was the argument in the original papers that proposed these experiments. One was based on quantum mechanics and the LOCC argument, local operations and classical communications cannot create entanglement. This is on a more general, theory-independent, meta-theoretic framework of constructor theory. And then there is the paper by Thomas and collaborators in GPT formalism. And while studying this subject, it became quite clear that what this local means has got nothing to do, or at least is not directly related to relativistic locality. But it's really the fact that, that the evolution breaks down in a certain form that is local with respect to the subsystems. So here, A and B are the two masses that are getting entangled. G is some system, and the evolution in time can be broken up in gates that act only on A and the mediator, and G and the mediator and B. And this is what locality means in this context. Classicality is some condition on the existence of this system here. And so the relation is not trivial. And so it's not clear if these theorems, for example, apply directly. So my question was, to what extent subsystem locality is an aspect of nature? Can we expect it from other things? Because after all, it seems to work most of the time. So when I do something to a chair, it seems I do it only to that chair, right? And often, the fact that the world is made of subsystems and you can operate on some systems, only certain ones at a certain time, it's assumed as a framework, and it's often motivated by relativistic notions that things that are far apart should not affect each other. So the question, basically, the broad question is, does subsystem locality hold in quantum field theory? Because these are, in a sense, these are our most fundamental theories of the world, the standard models and general relativity, say. And yes, does a field mediate interactions in the sense of quantum information, in that sense? And in what regimes does it hold, and to what extent is actually an exact property of nature? So here I'll talk to you about two ways to think about this that actually don't lead very far, and then one simple example that we figured out with Marius and Czaslaw and the collaborators. And then I just close with some open questions. So let's say that we have three systems, A, B, and C, and each they have their own Hamiltonian. And then A and C are coupled, and B and C are coupled together. And there is no direct coupling between B and C. Does this mean that the evolution is subsystem local? Does the system C mediate the interaction? Well, let's clump the operators such that some operators, it doesn't matter really where you put the single system operators. We just look at it like this. And the evolution in time is given by this formula, of course. And this is not equal to a subsystem local operation. It's not equal to a product of a gate that acts only on A and C and a gate that acts only on B and C. Because these two Hamiltonians will not commute in general. It is true that we can write it at arbitrarily good approximation as a product of two systems gates. Right? So it will hold at any degree of approximation. You can really approximate this evolution by a product of subsystem local gates. And maybe this is enough for the purposes that we need. We'll come back to that later. But there is no input from relativity here. This is just a true formula for any two operators. So I don't think it's a very insightful approach. Then here we have a counterexample. So let's consider quantum electrodynamics in the Coulomb gauge. Here we have two systems, two particles, two charge systems. This is the kinetic term of the radiation. Over here, there is the coupling of the systems with the radiation. And as you see, the two systems are not coupled together here. They're only coupled to the radiation. But then we have the Coulomb term, because we're in the Coulomb gauge. That is a direct interaction between the two particles, at least in this picture, right? And if we go to a regime where the particles are basically at rest and there is no radiation, this Hamiltonian is very well approximated by just the Coulombian term. And this means that no matter how far these two particles are, when you evolve in time, the gate that evolves them in time is a gate that couples them directly. So this is an example in which a theory that is relativistically invariant, there's causality in principle, it should be not possible to send information faster than light, does not satisfy that notion of locality from quantum information theory. So when does it do it? Well, we've managed to find a regime in which actually this works, and this is with this node that is on the archive, and it's a pretty specific setting. And it is two particles that are coupled to a massive scalar field in a specific regime that I will explain in a second. And basically, if you zone out for the next 10 minutes, this is what's going to happen. The evolution is subsystem local, but only up to some phases in the superpositions. And thanks to relativistic locality, in particular, thanks to the fact that commutators of fields at space-like separated regions vanish, thanks to this property, the phases are eliminated, they vanish, and we have relativistic locality in this regime. The regime of approximation is only, it says 3, but it's only two key assumptions, I would say. First is that the two systems have to be localized, the systems that are getting entangled, they have to be localized in separate regions of space-time. The wave functions should not overlap. And this is already an approximation because in general, the tails of a wave function are going to be extended all over space, so you have to either force the particles to be localized or just neglect the tails. And this second one, we use it in the computation, but I think it shouldn't be necessary, but I didn't manage to find a way to make it work without this assumption that not only are the wave functions restricted to a certain region, but they actually are a superposition of semi-classical states, like very localized, coherent states that don't get further entangled with the field. And this is kind of the picture. Here we have one system in a superposition of different trajectories that are controlled by some quantum qubit or qubit. And over here you have the system. The trajectories are far apart from each other. They're very peaked. They're like Zurich's pointer states. They don't get entangled. Like conditional on one of the branches, they don't get further entangled with the field. It's pretty late, but I will go through to a bit of the mathematics of it. Here is how it works. So this is the Hamiltonian for the system. We have some driven Hamiltonians for the two particles, A and B. It looks something like this, where there's a qubit, and conditional on the qubit, we have a time-dependent Hamiltonian. And this allows to model what you do in the lab, say like sending the particle in two different directions, or I don't know, whatever you want. But this is the idea of driving the particles given some qubit. Then we have the kinetic term for the field. This is just a standard thing that you see in all textbooks. And then we have a coupling, which is also standard coupling between the particles and the field. So it's local in space, and it's local in the sense that A only interacts with the field, and B interacts with the field, but A and B don't interact together. So this is the setup. And then we take a couple of approximations, which are the ones that I explained before. One is that there is no back reaction from the qubits. So there's no back reaction from the particles and the field on the qubits, and there is no back reaction from the field on the matter. So this means, like, if you formalize these assumptions, what you get is basically that the state of the whole system is a superposition of a bunch of states that are controlled by the qubits. And in each of these branches that are given by the qubits, we have the matter, the two particles are in some localized states, and the field depends on these particle states too. But in each branch, the field and the matter are not further entangled. And yeah, the Hamiltonian, we have an evolution for the particles. These are just the driven Hamiltonian, as I anticipated earlier, and also an evolution for the field, which is now it's written like this as a Schrödinger equation just for the field. These operators are acting only on the field, and they're given by, so this HRS is the expectation value of that interaction Hamiltonian, conditional on the states of the particles being like this. And we can write the evolution of the full system in this form. And let's look at this. This is not subsystem local, because there's a sum here. But if this unit evolution of the field would factorize in such a way, then you can shuffle the things around and you can write it in a subsystem local form. And so the next part after those approximations is to check whether this property actually holds. So this is the picture we had in mind. We have the particles in these superpositions, this evolution, and for each branch, we have this evolution for the field. And because the states are orthogonal, we can just look at one branch, and the evolution for the field in that branch is given by this Hamiltonian, and this is nothing else than a quantum field sourced by a classical source. So then you open a quantum field theory textbooks, and you look at this, and well, you'd have to do some manipulations, and you can actually find an exact solution for this problem, for this system. And it's given by this. There is a free evolution for the field. There's a displacement operator that basically writes information about the trajectories of the particles into the field. And then there is some phase, some term, that normally in textbooks this is thrown away. They don't care about this. But here we care about it because the phases are exactly what shows up in a superposition. So we look at this. We use the algebra for the displacement operator to break it up. And actually we get to this, which is really close to what we wanted. But we have these phases that are messing up the evolution. So if this phase was not here, this would have exactly the form we want. We could make these sums. We could just make these sums separately, and we would have a system that acts, an evolution that acts only on A and the field, and an evolution that acts only on B and the field. But we don't. So let's look at these phases. They look like this. They don't look great. But if you just look at them for a second, you realize that they are something like spacetime integral of two classical functions and the commutator of the field. This is the interaction picture field, which is the free evolution of the field. And remember what I said. We have microcausality, right? So those things vanishes when they're space-like. And we're basically there now, because if you look at this picture and you imagine these particles they're flying over here, if the time interval is short enough, this is the charge density of particle A, this is the charge density of particle B. So this part will only have support on the trajectories. But then if x and x prime are space-like in the whole integral, then that integral vanishes, right? So in other words, if the support of these two functions is space-like during this time interval, then the phase vanishes. This is in one branch, but if we have two branches, if we have all of the branches, then as long as this time interval is such that all branches are space-like separated from all the other, all trajectories are separated from all the other trajectories in all branches, then all of these phases vanish, and we get the factorization we wanted, and that's exactly the situation in which relativistic locality implies subsystem locality in this form. If the time interval is too long, and this is not true, you just break down the time interval. As Mario said, you just break it down in a number of evolutions, and then inside these things, it will break up, and so you will have a series of such evolutions. And actually, this is a physical interpretation. There's a free evolution of the field. Then you write onto the field the effect of particle A, and then you write onto the field the effect of particle B. And as long as the affected area doesn't overlap with the other source, it breaks down. Perfect? So in summary, perfect because I'm basically closing. As I said, there are different notions, they're related. We found a model in which the relation seems to be one way, it works like that you can find a regime in which subsystem locality holds, but it doesn't hold always. So we saw it with the example of the Coulomb interaction. Also, if just the particles are sitting on top of each other, the information will travel too fast, you won't be able to split the evolution that way. And I think this relationship that's not completely straightforward is an interesting question for this intersectional area of physics, for obvious reasons, because one is really native to relativistic studies and special relativity, and the other one is related to quantum information, so I think it's an interesting thing to study. The next steps would be exactly to see whether and how much this result can be generalized. I'm working on, obviously, to moving to massless gauge fields. I think I need to learn algebraic quantum field theory to make it work. Fortunately, we have experts of quantum field theory coming in the group. And, but the big question I'm asking you is, so if this does not hold, say that the standard model actually does not allow subsystem locality to be working exactly, does this impact the work that is being done in quantum foundations? Like, can we work with like an epsilonized version of subsystems or something like that? And with that, I thank you.